Hello everyone, welcome to MINDSPAN Education. In this video, we are going to look at few problems, whatever we have learned so far in continuous random variable. So let's look at the very first problem. We have given this Z, a continuous random variable with the probability density function. So this is the probability density function, and it has the probabilities within some interval, and out of this interval it has the 0 probabilities. We have to first find in part A what is the value of this gamma. In part B we have to find the cumulative distribution function, that is CDF, of this random variable Z, right? First of all, this PDF is not completely specified. Why? Because this gamma is unknown. In order to completely specify this PDF, we need to have this value also, that is gamma, which is unknown, and with this is what we need to find in part A. How we can find it is easy, right? We know the total probability should be 1. That means the total probability corresponds to the area under PDF, right? So that means integral from minus infinity to plus infinity. If we integrate the PDF from minus infinity to plus infinity, then that integration should give us the total probability, that is 1, right? We can make use of that and we can find this gamma, right? So let's do that. So part A. So you see the probabilities are 0 outside this interval, so we just can integrate it from -2 to 1, right? Otherwise, even if we consider from minus infinity to plus infinity, so those will be 0, which is not in this interval, so no need to consider that. You can simply take it from -2 to 1 and integrate this PDF over within this range, right? And this should be equal to 1. So now this is a simple integration. So gamma is outside. The integration of this would be Z plus ZQ divided by 3, and we have the limits from -2 to 1, that would be equal to 1. Now we can simply put the values, so that would be 1 plus 1 divided by 3 plus 2 plus 8 divided by 3, right? That would be equal to 1. Gamma times this will be 3 plus 1 4, 4 plus 6 10 plus 8 18. 18 divided by 3 is equal to 1. So from here we can see that gamma will be 3 divided by 18, that is 1 divided by 6. Now we have this gamma, so we have the PDF. Okay, once we have the full specification of the probability density function, now we can find the cumulative distribution function. And what is this cumulative distribution function? It is nothing but just the accumulated probabilities up to certain point. So we know from the definition of the cumulative distribution function, it is nothing but just a probabilities, finding the probabilities. So it is the probability that random variable takes the value less than equals to little z, right? And this we have called as a cumulative distribution function. So it will be the function of this little z, right? And how we can find this probability? To find this probability, we just need to integrate it from minus infinity from left side to till this point, so till a small z, right? And what we are going to do, we are going to integrate the PDF, so that will give you this probability, right? So let me first of all write, so gamma is 1 divided by 6, and since I have already used this small z for the CDF, right? So we can use any other variable, any other dummy variable, let's say x. So 1 plus x square dx, right? I hope there is no confusion that why I have written here x instead of this small z. If I write this small z, so what you will be doing, you will be end up with again the PDF will have the same variable, that is small z, and the CDF will have the again the same variable. So there would be confusion. So that what I have done, I have simply assumed that let's not use the small z since I have used here, so let's use some other variable as a dummy. So that is why I have used this x, right? So overall point is here that you need to find this, right? And whatever you will get by this integration, that will be the function of this little z, right? And one more point that you need to be very much careful. So this PDF is 0 outside this interval, right? And you have the PDF in certain interval, right? So you need to also take care of these interval while finding the CDF as well, right? So if you try to plot this probability density function, so we have taken this x as a dummy variable, so it is 0 outside these interval, so from minus infinity to till this point -2, and from 1 to infinity the probabilities that random variable will take the value have 0 probability, and it have some PDF that in the range from -2 to 1, right? Now if this small z is anywhere before this -2, so let's say it might be here or here or here, anywhere, right? And if you try to find this probability, right, the accumulated probability before this -2, so that will be 0, right? So we can directly write that the cumulative distribution function will be 0 for small z less than -2, right? Now for greater than 2, z greater than -2, we can take the z here or here or here or maybe anywhere up to whatever the point we want to calculate. So this z is a generic point, so let's keep it as a generic one, right? So z could be anywhere between this interval -2 to 1, right? So now this f cumulative distribution function, we will be integrating it from -2 to any generic point z, right? And we have this PDF 1 plus x square dx, and if we integrate, what we will be getting is 1 divided by 6 x plus x cube divided by 3 minus 2z, right? So 1 divided by 6 z plus z cube divided by 3. Here we will have plus 2 plus 8 divided by 3. So overall we will have 1 divided by 6 z plus z cube divided by 3 plus 14 divided by 3, right? So we will have the CDF that will be equal to 1 divided by 6 z plus z cube divided by 3 plus 14 divided by 3 within up to this range when z is greater than equals to 2 and less than 1, right? And for z greater than equals to 1, sorry, for z greater than equals to 1, so we will be taking any point that is greater than 1, so z could be anywhere, right? So what we have done, we have accumulated all the probabilities, right? If we go beyond this point, we have accumulated all the probabilities, and the maximum probability that we can accumulate is 1, right? Because beyond this point we have the 0 probabilities, and whatever the probabilities we have accumulated so far, we have already accumulated till here, right? So for z greater than 0, so this CDF will be 1, right? So if you want to find any probability between in this range, right, so you could take any point, right? Let's say if you want to find the probability, let's call this point P, or call this point small z. So you want to find the probability that random variable z takes the value till this point, that is small z. So what you are going to do, you are going to add this probability, that is 0, plus you are going to simply put this 2 here, right? And you will get the probability till this range, and you are going to add these two parts, so overall you will have the accumulated probabilities, right? Even if you try to put z is equals to 1, then so you, if you put in the CDF z is equals to 1, that means you have accumulated all the probabilities, right, till here. Because beyond this we have 0 probabilities, that means here till here we have accumulated all the probabilities. That means if I find the value of this CDF at z is equals to 1, then this should give me the total probabilities, that is 1. So you can put that 1 divided by 6, 1 plus 1 divided by 3 plus 14 divided by 3, right? So that would be 3 plus 1 plus 14 divided by 3, so that will give you 18 divided by 3, 6 will get cancelled, and you will have the 1. So just to verify and just to show you that how these CDFs and how these CDFs are actually nothing but the just the accumulated probability up to certain points. And also you need to be very careful if you have the piecewise function. Alright, let's move to next question. So what will be the answer to this part B? The answer to part B will be, let me write all the things at once. So the CDF is equal to 0 for z less than -2, and it is 1 divided by 6 z plus z cube divided by 3 plus 14 divided by 3 for z greater than equals to -2 and less than 1, and it is 1 for z greater than equals to 1, right? So this is the answer to your part B. Let's take another question, and this time we will be taking the question from exponential random variable. Okay, let's take another question, question number 2. So this is based on the exponential random variable, and we have already seen this exponential random variable. So let lambda be a positive number. The continuous random variable x is called exponential random variable with parameter lambda when it has the probability density function of this form. So we have already seen the PDF of exponential random variable. We need to find in part A the CDF of this random variable x, and we have already seen what is the mean of exponential random variable and what is the variance of this exponential random variable. And in part D we have to find the PDF, and in part E again we have to find the probability density function. We will talk more detail when we will reach here. So let's first of all start with this part A. So in part A, we just need to find the cumulative distribution function. We have the PDF, we need to find the CDF, right? The point to note here that it has the 0 probability when random variable takes the value that is negative, right? So we can directly write that the CDF value so CDF is 0 when this z is less than 0, right? So we just need to find for the positive part. So what will be the CDF when x is greater than 0? So how do we find? It is nothing but the probability that this random variable z takes the value that is less than equals to little z, right? And we have the PDF, we can simply integrate, and we need to integrate it from 0 to till this point. And before 0, we have already found that the total accumulated probability is 0. So we can simply integrate it from 0 to till this point, that is small z, right? So here we will have lambda e to the power minus lambda x dx, right? So this is simple integration, right? The integration of exponent, that would be again exponent so once you will do the calculation, you will get 1 minus e to the power lambda z, right? So overall you can write the CDF, that would be 0 when z is less than 0, and it is 1 minus e to the power minus lambda z when z is greater than equals to 0, right? So we have this part 1. We already know and we have already calculated the mean of this exponential random variable, that is 1 divided by lambda, and we also know the variance, and we have already calculated, and it would be 1 divided by lambda square. Now let's come to the part D. Right, and how we have calculated, you can just look at my previous lecture. There I have explained how to calculate the mean and the variance of this exponential random variable. You can refer the previous lecture. Now in part D, suppose x1, x2 and x3 are independent exponential random variable, each with parameter lambda. Find the probability density function of this random variable z, and this z is a maximum of x1, x2 and x3, right? So we have given that these 3 random variables, and these 3 random variables are exponential random variable and they are independent, right? So and this we have defined a new random variable, and this is how we have defined a new random variable based on the existing random variable, right? And we just need to find the PDF of this random variable, right? So we have the info about these random variables x1, x2 and x3, and they are the exponential random variable. So if we have to find the PDF, what we can do, we can simply find the CDF first of all, because how CDF is defined, CDF is nothing but if we want to find the CDF of this random variable z, right? Once we will have the CDF, we can simply differentiate the CDF and we will have the PDF, right? So what is cumulative distribution function of this random variable z? So it is defined like this. So random variable, we just want to find the probability that random variable z takes the value less than equals to little z, right? And this is what the CDF of this random variable z, right? And how we can find this probability? So z is nothing but the max of this. So we can write at the place of z that the max of random variable x1, x2 and x3, and it is less than equals to little z, right? So we are going to make use of this, that these random variables are independent, right? First of all, let's look at this expression, that the max of these three is less than z. What does it mean? So what I want to do is, so if the max is less than equals to z, can I say that each of the x1, x2, x3 will also be less than equals to z? So we have given that the max is less than equals to z. Can I say that each of one will be individually less than equals to z? You can see, you can verify this. So this function will give you the maximum value out of these three, right? So let's say this max is here somewhere, and max will be one of from x1, x2, x3, right? And we have given that the max is less than z. So where will be this z? So z will be somewhere on the left side, right? Because whatever the maximum, and that, sorry, let me go on once more. So the max is less than z, right? So whatever the maximum value, so let's say call the maximum value as max, right? So the max is less than z, so z will be somewhere around here, right? And if max is here, so whatever the other number that is not max will be less than this max, right? So each of the number will be less than also z. So we can write this as that if max of x1, x2, x3 is less than z, then each of these will individually less than z. Are you able to digest this? You can take it simple. This is real line, right? This function will return a maximum value. Maybe it will be x1, x2 or x3, whatever. So let's call that number is a max, and we have given that whatever the maximum value that will be returned, and that is less than z. So z will be some around here, right? So because whatever the maximum number will be less than this z, right? And if this function is returning the max, so other number, whatever the other things will be there, that will be less than max. So although other number will be this side, right? So ultimately I can say that each of the individual will be less than z. And what's the benefit of doing this? The benefit of doing this, that since these random variables are independent, then we can write these joint probabilities as the product of their individual probabilities, right? So that will be the product of individual probability. That probability random variable takes x1 takes the value less than z times probability that random variable x2 takes the value less than equals to little z, and probability times probability that random variable x3 takes the value less than equals to little z, right? And what are these? These are nothing but the CDF of each of the, so this is the definition of CDF, right? That random variable takes less than equals to certain value, right? And this is the CDF of this exponential random variable, this is the CDF of this exponential random variable, and this is the CDF of this exponential random variable. And we know the CDF of each and every exponential random variable, that is this, right? So we can write this as 1 minus e to the power minus lambda z to the power q, right? And once we have this CDF, so we have got the CDF of this random variable z. How we can find the PDF? So we can find the PDF, so this is CDF, so we can find the PDF just by differentiating the, so what will be the PDF? So PDF will be 3 times 1 minus e to the power minus lambda z, and we will have in front of minus 3 lambda also, right? So let me write so this is the CDF, and the PDF, that is of this random variable z, that will be, so again this is exponential random variable, so it will be 0 when z is less than 0, and we just need to differentiate this, right? So that would be 3 lambda e to the power minus lambda z times 1 minus e to the power minus lambda z, and this is when z is greater than equals to 0. Here we will have a square also, right? So you know how to differentiate this one, right? I am not going to differentiate, you know very well that how to differentiate the exponential. All right, okay, now let's come to this part E. So part E, we have another random variable, that is w, and we have to find, and this w is defined as that mean of x1 x2. How we can find? Again, from the given info, these two are exponential random variable and these two random variables are independent. So how we can approach? Simply we can first of all find the CDF. So CDF is nothing but finding the probability that random variable w takes the value that is less than equals to little w, right? And we can write the similar thing. We can replace this w by the function that min of this x1 x2 less than equals to little w. Now can we say that if min of x1 x2 is less than w, then each one will be less than w? No, each of one will not be less than w. So this function will return the minimum value, right? So minimum will be somewhere around here, right? And this, whatever the minimum we will get, and that will be less than w. So if it is less than whatever the minimum we are getting, that is less than W, that means W will be somewhere around here, right? And we have got the minimum out of all these argument, then whatever the value that is here apart from this mean will be greater than this mean. So that value may be here or here or here or here, so that value might be greater than this W. So we cannot say that if mean of x1 x2 is less than W, then each individual will be less than W. What we can do? We can write this same thing, the probability that mean of x1 x2 is less than W. We can write the same thing, that 1 minus probability that mean of x1 x2 will be greater than equal to W. Now again, if I ask you that if mean of x1 x2 is greater than W, can I say that each individual will be greater than W? So if mean is, so mean will be somewhere around here, and if it is greater than W, so W will be somewhere around here. And if this is mean, if any one of is the mean, the other values will be this side, right? So each one will be greater than W, right? So we can write 1 minus probability that each of one, that x1 will be also greater than, if mean of x1 x2 is greater than W, then each of one, that is x1 will be greater than W, and also x2 will be greater than W, right? And these two random variables x1 x2 are independent random variable, so we can write each as a product of individual probabilities, right? So let me first of all make some space. Okay, now how we can proceed further? So this we can write, because we know the CDF of the exponential, right? So somehow we need to turn these into definition of CDF. So how we can write? So that will be 1 minus probability that random variable x now is less than W, right? Similarly, we can write this as 1 minus probability that random variable x takes the value less than W. We know this. What is this? This is nothing but the CDF of exponential random variable. And what is the CDF of exponential random variable? So this one, right? So this one will get cancelled. Overall, you will have e to the power minus lambda W. So here we will have 1 minus 1 will get cancelled, e to the power minus lambda W, and from here also you will get 1 will get cancelled, and e to the power minus lambda W. So overall it will be 1 minus e to the power minus 2 lambda W, right? And once you have the CDF of this random variable W, you can have the PDF. So what will be the PDF? So PDF of this random variable W will be 0 when W is less than 0, and it will be e to the power, so it will be, let me, so 2 lambda e to the power minus 2 lambda W. So what I have done, simply I have differentiated this when W is greater than equals to 0, right? So this is the probability density function of the random variable W. Alright, so we have solved, I think. Okay, I think these were few questions, and the part D and the part E, I think you must have learned something new. Okay, that is all in this video. We are going to move into the new that we are going to discuss in next video. Alright, so I think I can say almost 55 to 60% we have covered the probabilities, and we are expecting to finish it up before the 15th of June. Hardly it will go 20th of June, so I will try to finish it up as soon as possible. Thank you so much.